section 6.5, graphs of polar equations. Now, we ended the first part by creating a graph of a cardioid, and what I didn't do was show you what it looks like in the graphing calculator. So let me do that first. So here I already have it drawn on the 84. Now, first thing you want to make sure is you have your calculator in polar. As you can see, it's been switched from function to polar, and that it's in radians. So if you're using an Inspire, make sure you change your degrees to radians and choose function mode polar when you go to graph it. So when you go under y equals, you're going to see you have r's there, and for the 84, your variable key will give you its theta. So there is our first graph. And then what I did for my window settings is my theta goes from 0 to 2 pi. My step is small, about 0.13 is what it usually defaults to. And then I hit zoom trig, so it gave me these numbers. If you do -10 to 10 for both x and y, you'll be fine, so that your graph will look something like that. And you can see it matches what we did, and you can see the symmetry there. Now, if this had had 1 plus cosine theta, this graph would have been rotated along the x-axis. So it would have been lying this way. This would have been down this way. So half of it would have been above, and the other half would have been below, like that. So it just depends on whether you're using sine and cosine. And that's going to go for all of these graphs that we're going to do. All right. So that is part of a Lee-Misson curve, the cardioid. So let's do another one. So our next graph, we're going to start again by checking the symmetry. So we're going to start with our polar axis. So our polar axis. And we're going to take r equals 2 plus 3 cosine negative theta. And hopefully you guys realize some of these you'll learn after a while, that because you understand whether sine and cosine are even or odd, which ones these will have. Since cosine is an even function, this does have polar axis symmetry. So if we check the line symmetry, because some of them can have more than one type of symmetry. What we're going to find for this one is we're going to have r equals 4 plus 3 cosine pi minus theta. And so that's going to be 4 plus 3 times using our difference identity. So we're going to have cosine pi, cosine theta, plus, I'll put it down here so it doesn't run into our table, sine pi, sine theta. So the first part, that's -1. This is 0. So we will have r is going to equal 4 plus 3. Actually, it'll be -3 now. -3 cosine theta. And you can see that this is a big no. And then finally, pole symmetry. Come on, there we go. We're going to do -r equals 4 plus 3 cosine theta. So moving that negative sign, you can definitely see that they are not equal. So this is also no. So when we pick points, we only need to do above the x-axis, because then we can reflect them below the x-axis. So I'm just going to use 0 to pi, because that will that will work perfectly. So here's my theta, my r, so 0, pi over 6, pi over 3, pi over 2. Then we go to 2 pi over 3, 5 pi over 6, and then finally pi. Now, I've been skipping the pi over 4 angles just so it doesn't crowd the picture. You can definitely include them. There's nothing wrong with using more points. Okay, so substituting 0 in. So again, let me write our equation down here. We have r equals 2 plus 3 cosine theta. So putting 0 in for theta, that'll give us 1. So we have 2 plus 3, which is 5. That's for the first one. Pi over 6, we're going to have 2 plus 3 times the square root of 3 over 2. And that is going to give us 4.6. Pi over 3, we're going to have 2 plus 3 times 3 over 2. Oh, I'm sorry. Reading my notes would be, I misunderstood what I wrote, 3 times 1/2, which is going to give us 3.5. You can see we're getting smaller. So pi over 2, cosine of pi over 2 is 0, so we just have 2. 2 pi over 3 is going to be 2 minus 3/2, which is going to be 0.5. And pi over 6 is 2 minus 3 times the square root of 3 over 2, which is negative 0.6. And finally, at pi, we're at negative 1. And again, go through and check those to see how they turn out. Okay, so what we're going to do is exactly what we did the last time. We're going to plot these in order, and then we're going to reflect them and draw them in order as well. So when we're at 0, we're at 5. So let's see, how do I want to count these because they're kind of small. All right, 1, 2, 3, 4, 5, right there. Okay, there's 5. And then at pi over 6, we're at 4.6. So we're right there. And then at pi over 3, we're at 3.5. So that's going to be right there. And then at pi over 2, we're at 2. And then at 2 pi over 3, we're at 0.5. So that's like way in here. And then at 5 pi over 6, we're at negative. So we're on this side, actually. So we're like right in there. And then at pi, we're at negative 1, which is right here. Because it would be over here, and then we have to reflect it back. Okay, so drawing that, here's what we have when we draw it. We have, let me use green so you can kind of follow it. We go up around like this, we come around like that. Okay, and then we're just going to reflect those, so the pi one will stay where it is. Same with the 0 one. Then we are down here, we are here, we are here, we are here, and then like that, here. Okay, so drawing that side, we have this then. Like that. Okay, so this is called Lie Mason with an inner loop. This is a French word. You have the cedilla there. That's why it's pronounced Lie Mason. Lie Mason with inner loop. So well, you're going to notice that inner loop has a length of 1 unit and the outer loop has a length of 5 units. And we're going to learn how you figure those out. Hopefully you guys are following along with that. So now we have two different lemmasins. We have our cardioid and we have an inner loop. So looking at our graph, I did this one on the Inspire. That's what you would get on the Inspire. So you can see it there as well. Okay, and again, if I pull up my entry, I changed my mode to polar. My theta goes from 0 to 2 pi. My step just defaults to 0.13, which is fine. And I have that beautiful loop there. If you notice, it's on the x-axis. If I'd had sine instead, it would have been oriented like our cardioid on the positive y-axis. So it would have looked upside down, so to speak. It would have been oriented in this direction like the cardioid. But that is a different type of lemmasin. So here's one more lemmasin that we're going to do. And again, we'll start by checking for symmetry. So we'll start with polar axis. And I can say already that this is, yes, going to have it because we're dealing with cosine, but let's go through it. So we're going to have r equals 4 plus 3 times cosine of negative theta. And since cosine is even, that will stay positive. So this is a big yes. See, after a while, you don't have to write these down. You can look at them and go, oh, this has polar axis symmetry. Does it have line symmetry? Now, it makes sense that it would not because it's a cosine function. So I'm just going to write no here, and you guys can go ahead and double check that on your own. But think about the fact you're splitting it down the y-axis. Think about the sign of cosine in quadrant 1 compared to quadrant 2. So if you want to, you can go through and substitute in pi minus theta and see if you get the same result as you would for just theta. And then finally, pole symmetry. We're going to substitute negative r in, and again, you're going to see that this does not have pole symmetry, which makes sense because cosine, again, is an even function. So we're going to use the same angles we did before. We're going to go from 0 to pi, because that'll give us everything we need to reflect it. So we're going to use 0 pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and then finally pi. And then substituting in our equation, we are going to have, for the first one, when theta is 0, we're going to have 4 plus 3, because cosine of 0 is 1, so we have 7 units. And then 4 plus 3 times the square root of 3 over 2 is going to give us 6.6. And again, you can see that we're going to get smaller. And at pi over 3, we have 4 plus 3 times 1/2, so 3/2. So that's 5.5. At pi over 2, cosine is 0, so we're just going to have that 4. 2 pi over 3, we're going to do 4 minus 3/2, so we get 2.5. And then the next one is going to be 4 minus 3 times the square root of 3 over 2 at the pi over 6 angle. So we get 1.4. And then at pi, we're going to have cosine of pi, which is negative 1, we'll have 4 minus 3, which is 1. So graphing this one in the same way, we start at 0. So we have 1, 2, 3, 4, 5. This will be 6. So 7 is right there. And then going to 6.6 of pi over 3 will be about there. And then pi over, I'm sorry, that was pi over 6. So pi over 3, we're at 5.5. So that's going to be here. I screwed that last point up. That point should be out here. These circles are so small. So then this will be here. There we go. Better. And then at pi over 2, we're at 4. At 2 pi over 3, we're at 2.5. So we go way in here at this point from 4. So 1, 2. So like right there. And then at 5 pi over 6, we're at 1.4. So there's 1, 2, so right there. And then at pi, we are at 1, which is right there. It's kind of hard to see. And then we are going to reflect all those points, but let's draw this first. So starting at 0, like that. And now we're going to reflect all of these points. So the one on pi will stay there, and then we have this one, and then we have here, and then here. Oops, I went out too far. 1, 2, 3, 4. And then like that. Okay, and then drawing the bottom side, we have this. So it's not quite a heart. So this is called a limacin without an inner loop. And there are 2 types of those, and this is one that's really called that it has a dimple. And then there's some that just are flatter, because this kind of goes in a little bit there, like that. This has a dimple. And then there's ones that just have a flat side, and they look almost circular. They're called a convex limacin. And what we'll notice is the length, the longest length we have is 7. So let's summarize our limacins. So we have our cardioid, and I forgot an I in cardioid, and our inner loop, and no inner loop. So here's what we're seeing. There's a lot of similarities, but we have 2 types, one with cosine, one with sine for each of these. So our equations are going to be R equals A, and we can have plus or minus B cosine theta, or we can have R equals A plus or minus B sine theta. That just changes the sine and cosine, changes the orientation of it. The plus or minus flips it from one side of the axis to the other, so on the positive side or the negative side. One thing we want to remember, we always think of A and B as being positive numbers. And then what makes it a cardioid is the ratio of A over B is 1. So with that, we have a domain of all real numbers, because sine and cosine have no breaks in them. Our range is going to be from A minus B, that's our smallest range, to A plus B. And looking at our symmetry, for our sine one, this has line theta equals pi over 2. And for our cosine one, so we saw the sine one, we didn't see the cosine one. it's going to be flipped on its side. It's going to have polar axis symmetry. Let me use another color here so it's easier to see it. And then finally, I want to note here that we do have a max R value, and we want to look at the positive length, and it's A plus B. So in other words, you ignore the sign in front of B. Okay, then when we have an inner loop, our equations are going to look the same because they're basically the same. What changes that is whether or not the ratio of A to B equals 1, greater than 1, less than 1, that kind of thing. And again, A and B are positive, and now the ratio of A over B is less than 1, and that's when you get the inner loop. The domain and range are the same, so what I'm going to do is I'm just going to draw a line here that indicates that these go the whole way across. So I don't have to write them every time. You can if you want to. Our symmetry is a little different. So our symmetry, again, depends on which equation you're using. So for the sine, we have the line theta equals pi over 2. And then for the cosine, we have polar axis symmetry again. And in this case, we have a max R of A plus B. And that is again the length of our outer loop. And our inner loop is going to be the absolute value of A minus B, because it's positive. It has to be positive because it's a length. And then finally, if we don't have an inner loop, so we have our two equations again. They're all going to have the same equation because they're all part of the same family. And A and B are always considered positive. And now the ratio of A over B is greater than 1. Now if it's between 1 and 2, it has the dimple. If it's 2 or greater, it's kind of flat on that side. And you'll see those as we go. Same domain and range. The symmetry is going to be the same as well. So if you have sine, because these are all part of the same family, you're going to have pi over 2 symmetry. And if you have cosine, you're going to have polar axis symmetry. Now this doesn't have an inner and outer loop, but again, we have a max value of A plus B. Okay, so I'm going to stop there, and then in the last video, we're going to talk about our last family, which is rose curves.